Okay, and now for something completely different, although this has to do with this is not a protoplanetary disk. And to make that clear, the debris disk of the sun is evinced by zodiacal light, which is finely divided dust that basically arises from collisions in the asteroid belt. And the sun does not have a protoplanetary disk, period. I don't think anyone will argue that. So planetary debris disks are second generation disks that are produced after a planetary system has become relatively mature, and they result from collisions of small bodies in the system that then produce a lot of debris, which eventually crushes itself down to finely divided dust. We see as either scattered light or infrared or millimeter wave light. So we've already seen this plot a couple of times in this conference. This is sort of bragging rights to exoplanet searches, but you'll notice to the lower right, there's a big blank spot. And debris disks let us investigate that blank spot. And they also let us go down to, as I've already mentioned, very small objects in planetary systems that show in the two areas that debris disks explore uniquely are shown by these two ellipses. So in the first press conference for Spitzer, this was what we showed off. This is the debris disk around Fomalhaut. And what was really exciting was we resolved it, and it showed that a lot of the flux was coming from inside the outer ring, which had been previously observed in the submillimeter. When we delivered MIPS, we had a big party, and I had to stand up and give a speech. And at the end of the speech, I said the real test of what we have done, because I was aware of the limitations of Spitzer and MIPS with a pretty small telescope and one filter band in the mid-infrared. The real test will be if astronomy goes ahead and builds something to work in the mid-infrared that is far more ambitious and impressive than Spitzer and MIPS. And there it is. So this is the Fomalhaut disk at basically the same wavelength as observed with MIRI on JWST. And well, I have a little bias, but please, let's all pause and just admire it a little bit. It's a really spectacular image. So this is what I like to call the assembly diagram. This is where we take the JWST image and we stack on top of it in blue the HST image, and then in red the ALMA image. And those are the three images that are available at sort of arc second or sub-arc second resolution. There are no other images at that resolution, but it kind of shows you how they go together. And this is all of them stacked. And so we can diagnose this image to see what's going on. The ALMA ring is where what's called the parent bodies are circulating. Now, don't imagine those as great big bodies. Those are sort of sand-sized bodies, which are then colliding with each other to produce smaller grains. They, of course, have to come from larger bodies that are running into each other and creating a lot of debris as a result. They also collide and they produce much finer particles, and basically to scatter efficiently, the particles have to go from sand size down to submicron size to see in the visible. And you can see the radiation pressure from the star is blowing those much smaller bodies out of the parent body ring. And so you can see the HST image shows a little halo coming out around the ALMA ring. And the MIRI image shows that dust being flowed further out. But what's really fascinating is the structure inside. And the easiest way to explain that is there must be a planet or two inside there. It's already thought there are probably a couple of planets that are shepherding the parent body ring, because it's very hard to understand how the ring could be so narrow and well behaved without that. And we may have found evidence for more planets in this system. And in fact, this is an illustration I really like. This is a rather old paper speculating about the debris systems in the solar system. And there's this great quotation. This is the calculation that Lilienthal carried out. And you can see that, particularly Neptune, there's a very characteristic ordering of the debris in front and behind Neptune on its orbit. And you can read the quotation: if an extraterrestrial intelligence were observing our solar system and had the image in this figure, it would know if its knowledge was similar to or better than ours, and to observe it, its knowledge would have to be a lot better than ours. It's a side comment that at least one giant planet at about 30 AU exists in our solar system, i.e. this would result in the discovery of Neptune by this advanced civilization. And that's kind of what's going on inside the Fomalhaut outer ring. Now we can speculate about what's happening farther inside, because the inner out to maybe 8 AU is kind of blocked out by the saturation due to the star. Already we've seen hints of 3 planets. I think we can eliminate the idea that there might be a massive planet inside of that region that's covered up by the saturated part of the image. This is a study of all the known debris disks that have, all the known planets that have masses of Saturn or greater mass out to 10 AU, and I'm looking at the W3, WISE W3 minus W4, which is basically a measure of the warm infrared excess. That is what you saw so beautifully in Fomalhaut. It's where there's finely divided dust that's inside the outer ring. And you see where Fomalhaut is, it has quite a large warm excess. You also see that none of the other stars that have massive planets around them within 10 AU have any significant access like that. And I think this is because when massive planets get a little restless and they start to wander, it's very destructive to debris disks. And in fact, we know when Jupiter, all the theories about Jupiter, Nice model, Grand Tack, whatever, result in really throwing material out of the asteroid belt in huge amounts, like 100 to 1 loss in the asteroid belt. And this may be functioning around a lot of other stars with massive planets. Okay, this is a pre-publication image. I should say the Fomalhaut image and all of these images were produced by Andras Gaspar, who's become really adept at PSS subtraction, and he was the lead author on the Fomalhaut paper. H2 is the lead author on a paper on Vega. And I think you can already tell, what does this tell us about this planetary system? Very smooth. So there are probably not very many planets lurking around inside the outer ring in Vega. There is that subtle, it's not a gap, it's sort of a dip. That can result from a mean motion residence of a planet that's actually outside the debris system. But it's going to take a lot of calculation to test whether that's actually what's going, but that might be going on, but that might be a hint there's a planet somewhere. But basically, there's just not a lot of evidence here. And there we go. This is, I said preliminary. This is actually pre-preliminary. The data is about 2 weeks old, but it's those, the Epsilon Eridani disk. And we can already tell it's like Vega. It's very smooth, and there's not a lot of evidence for unseen planets lurking around in that disk either. And if we put them on the same plot, we can probably eliminate massive planets. And this is interesting because Epsilon Eridani has a confirmed planet at 3.8 AU, which we don't really see in the debris disk, but that may be a resolution problem rather than that there's not some area that's carved out, because it's very close to the star. But the evidence is it's probably not a really massive planet because it has large mid-infrared excess, just like Fomalhaut and Vega do. Now, for a bit of a switch, those of you will remember Fomalhaut is supposed to have a planet, Fomalhaut B, and Andras Gaspar, when we were preparing a proposal, downloaded all the data, including data that hadn't been published, and found that the planet was gone. And so there are various frames of the evolution of the planet from the discovery frame to the the left in the subframes. And if you can look closely enough, you'll see that in time it got to be a little extended. Actually shows in Paul Callis's simulations, but he was so convinced it was a planet, he didn't actually point this out. And then finally in the last frame, it can't be detected. It had grown large enough that it was basically a surface brightness problem to pull out what was the planet. And we think this is the product of a collision, like the collisions that produce the debris in other debris disks, but on a smaller scale. And there are other systems where there's a lot more going on in what we call extreme debris disks. These are stars that are something like 25 to 100 million years old. So they're still in the process of forming terrestrial planets with collisions and so on. A little bit like the collision that formed Mars with an object that hit the Earth. And some of these stars are extremely variable in infrared excess. Look at the top, V488 Perseus is bubbling along. This is the excess above the star at 3.6 and 4.5 microns. This is form Spitzer data. And then you see there was a huge collision way over just before Spitzer was decommissioned. A great increase in the amount of dust around that star. And look at the temperature around this star. It was bouncing along. And when that big collision occurred, the temperature between the color temperature between these two bands shot way up. And in fact, every time there's an increase due to a collision, there's an increase in the color temperature. Another example is NGC 2547 ID8. And this is one that is almost in the Spitzer constant viewing zone, so we can monitor collisions with great detail. And in contrast with V48 Perseus, you can see the temperature stays pretty constant through all of that activity. But what you're seeing around both of these stars is asteroid-sized objects crashing into each other, and then the consequences are the release of a lot of dust. What is really interesting is V48 Perseus is a low-mass star, and the dust is spiraling into the star, whereas ID8 is a higher mass star, and radiation pressure is pushing the dust away from the star, and that accounts for the different temperature behavior. When you had a lot of dust with V48 Per, it falls into the star, it gets warmer, whereas the radiation pressure means the dust is ejected from the radius where it was produced, and so it gets cooler and it basically doesn't change the signature. And then this is MURI spectra of some of these systems, and it shows a big variety of, but basically materials produced under extreme conditions. The sort of double humped peak that's kind of dominant in this is crystalline silicates, which get produced from the high temperatures of the eject in these collisions. A little to the left of it, there are two peaks, and those are from silica smoke. It's very finely divided dust, which get condensed out of basically gaseous silicate material from even higher temperatures. V48 Per is unique in their little hints of carbon silicide in its spectrum, but it's kind of low contrast. And Kate just emailed me a day ago. We have another cycle on it, and the spectrum doesn't seem to have changed. But there's a lot of variety in these systems that reflects the extreme conditions in the collisions. And that's just part of adding to the fun of studying these systems. So, go back to the beginning. With MURI, we can fill in the regions indicated by these ellipses. You can look for traces of planets that are below current detection limits. Planets down to Neptune are a little more massive, probably will carve gaps in these rings. As I indicated earlier, there might be effects of mean motion resonances on the structure. Now, that all has to be modeled, but basically we're starting to get indications that it isn't that common to have planets even of sort of Neptune-ish mass around the nearby stars. And the violent collisions that build and destroy planets, we can document by looking at the variability and looking at the materials that are produced in the breaking up of the asteroids around these stars. So thank you, and I hope there's some questions.